Hello, this is Nick of Time. Welcome to this, our 17th talk on the physics of time. Today we'll talk about general relativity and time. Most of us have heard that in general relativity, gravity is supposed to provide a curvature to space-time, both space and time. So this graphic gives a representation of curved time. First, we'll look at general relativity's time dilation. Well, it's quite different than special relativity's time dilation. In fact, they're so qualitatively different, it's unfortunate and really misleading to give them the same name, time dilation, as they're really very different constructs. General relativity's time dilation does not have any inherent logic problems. In addition, general relativity's time dilation does not disagree with the empirical data. So this is very different than special relativity time dilation as well. So we have no problems with general relativity's time dilation. What is general relativity's time dilation? Well, it says clock rate is a function of gravitational potential. As gravitational potential energy of a clock increases, its rate also increases. All right, let's go, this is a little bit of an aside here. I'll make a couple of points. General relativity's time dilation is a physical effect, an asymmetric effect. When an object increases in its potential energy, its clock rate also increases. So it's not an analog to the special relativity time dilation equation. And the real difference here is the difference between being asymmetric and the special relativity time dilation equation being inherently symmetric. Further, general relativity and special relativity have different space-time models. And this was a major obstacle for relativists trying to create a seamless merger between the two theories. Now this is just, the third point is just my speculation, my personal opinion. There's no QED logic that leads to it or overwhelming empirical data forcing this conclusion. But my opinion is that Lorentz relativity clock retardation is a better analog to general relativity's time dilation. They're both asymmetric in form. Further, I think that Lorentz relativity's model of space and time is more compatible with the general relativity model, except to the degree when people start adding the special relativistic aspects to the core general relativity model from the gravitational field equations. But again, and let me make a point about critical thinking here. Critical thinking isn't restricted to coming up with hard and fast QED logic or just showing overwhelming empirical evidence. Critical thinking is just having an open mind and looking and not just taking for granted that the currently accepted theory is true or what a person of authority says is true. So the first step is often doing some thinking, some speculative thinking. But it's labeled as speculative thinking. It's like, hey, here's an idea, let's try it out, let's examine it, let's test its logic, let's see how it matches the data or doesn't match the data. So basically, everything's fine with general relativity, with time dilation, but, and here's the key point for this talk, as a segue to our next section, which will be talking about going beyond relativity in terms of how to treat time. General relativity's block universe of space-time is a four-dimensional static block. Pictorially, here's a relativist model of that. You can think of it as an ice cube with various paths etched into that block, and static paths. And here, time goes from the bottom of the picture to the top, and then there are orthogonal two-dimensional planes of space, orthogonal to the time axis. Okay, let me just get here. And here's the main point of this talk. General relativity removes the essence of time. Now, Lee Smolin is a professor of physics. He's an ardent relativist, mainstream physicist, happens to also be a critical thinker, which is excellent. But here he's talking, and most relativists would agree with his assessment of general relativity on this topic. These are quotes. General relativity treats time as if it were another dimension of space. Normally we think of time as flowing and having that unique property, but not in general relativity. It's like a static dimension of space. Second point, general relativity gives a description of the whole history of the universe as a mathematical object, which is timeless. Third, in general relativity, time has become spatialized or geometricized, basically a static dimension. So the key point again is general relativity removes the construct of past, present, future, which we tend to think of as kind of an essential property of time. And that's what we're going to try and put back into physics when we continue our series of talks. So thank you very much for joining us on this talk, and hope to see you next time.